Welcome to the Deep Dive Books channel, where we hope you find something valuable every day.
Let's continue exploring Max Bennett's A Brief History of Intelligence. This is the fourth part of our discussion. Before discussing each breakthrough of the brain, Bennett always introduces the evolutionary history of the relevant animals. While reading these evolutionary histories, one impression stands out. The brain's evolution is accelerating, with each structural change becoming smaller, yet the new functions resulting from these changes are increasingly remarkable. In the past, it took billions or hundreds of millions of years to achieve a breakthrough. Later, breakthroughs occurred within 1 or 200 million years, or even tens of millions of years. Vertebrates, even fish, already possessed most of the basic structures found in today's brains. Subsequent breakthroughs involved minimal structural changes, but even a small change could lead to a significant new function. But the cost of evolving that new function was immense. It would mean not only a drastic change in the environment, but also a global extinction of species. Yes, Earth's life forms had to undergo several mass extinctions for us to become who we are today. Without those extinction events, we might still be some kind of fish, living comfortably in the ocean. In the last part, we mentioned that our vertebrate ancestors were a type of fish living in the ocean. From here on, instead of saying our ancestors, let's just say we, referring to the species along the line that eventually evolved into humans. It makes the story more engaging. Initially, we lived quite well in the ocean, so why did we move onto land? We were forced to. First, plants began to colonize the land because it offered better conditions for photosynthesis. These plants rapidly occupied the continents, growing from a few centimeters to several meters tall, like trees today. If you had viewed Earth from space back then, you would have seen vast green landmasses. While this might sound nice, it actually caused a big problem. The rampant growth of plants disrupted the balance between photosynthesis and aerobic respiration. The plants consumed carbon dioxide and produced oxygen at such a fast rate that the Earth's carbon dioxide levels plummeted, leading to global cooling. And it wasn't just a little cold. The oceans froze, making it difficult for life to survive. This led to a mass extinction, about 375 million years ago, at the end of the Devonian period. Ironically, while we are currently worried about having too much carbon dioxide, it's worth noting that 2 historical mass extinctions were caused by too little carbon dioxide. Perhaps plants are the ultimate force behind carbon neutrality. To survive this mass extinction, many animals had to leave the ocean and move on to land. This is how we evolved lungs to breathe air. It was a gradual process of adaptation. At first, we used both lungs and gills, allowing us to breathe in both air and water. We stayed near water sources on land, and gradually, we lost our gills, our fins turned into limbs, and we became land-dwelling tetrapods. At this point, our ancestors faced a major divergence. Some remained cold-blooded and became the ancestors of today's reptiles, while we evolved into warm-blooded animals. This strategic choice had both advantages and disadvantages. The benefit of being warm-blooded is that our body temperature remains constant, allowing us to stay active, even when the temperature drops at night. This means we could hunt at any time. In contrast, reptiles' body temperatures drop with the nighttime chill, making them sluggish and difficult to move. So, when night falls, don't they all become easy prey for us? However, the downside of being warm-blooded is that we require more food to maintain our body temperature, whereas reptiles need less. It turned out that this strategic choice was initially correct. We evolved into Therapsids, which were about the size of a tiger and looked somewhat like lizards. We even invented fur to keep warm. At that time, the land was rich in food, and the often sluggish reptiles were no match for us. For the next 50 million years, we ruled the world. Life seemed good. Until about 250 million years ago, when Earth experienced another mass extinction. This was the most severe extinction event in Earth's history, where 96% of marine species and 70% of terrestrial species died within 5 to 10 million years. Scientists don't know the cause of this extinction. It might have been an asteroid impact, volcanic eruptions, or something else. This extinction nearly wiped out the Therapsids, because food was so scarce. The reptiles, which required less food, were more likely to survive. They evolved into dinosaurs. The world that followed belonged to the dinosaurs. They would dominate Earth for the next 150 million years. It seemed that the reptiles had the last laugh. But fortunately, some of us survived. To survive in the cracks of the dinosaur world, we developed two characteristics. We lived in burrows, and the most significant trait was that we became smaller. This animal is scientifically known as cynodonts. We went from being the size of a tiger to the size of a mouse. We became so insignificant that we didn't dare leave our burrows during the day. We had to wait until the cold night, when the dinosaurs were less active, before venturing out to find food. Initially, we only dared to eat plants, but we eventually progressed to eating insects, and some of us even learned to climb trees. We once had a glorious moment, but now we had to endure. We survived like this for 150 million years, without any hope of seeing the light of day. Yet, the gods of evolution favored us once again. During those long, ancient nights, we quietly evolved from Therapsids into mammals. We gained a competitive advantage. When it comes to muscle strength and speed, as mammals, we were far inferior to dinosaurs and birds. It was extremely dangerous for us if we were discovered. But our advantage was that we could strike first. We sometimes hid in burrows, sometimes in trees, not provoking anyone, like submarines waiting for the right moment. When a nearby insect or other prey appeared, and the dinosaurs and birds were at a distance, we could quickly make a move, capturing our prey, and returning home before they even noticed. Isn't that advantageous? Strike first. But take note. To accomplish this, you need two important conditions. The first condition is that your vision must be excellent. This only matters on land. In water, no matter how good your vision is, you can't see far, so playing the submarine trick doesn't work. That's why fish don't study this technique. But on land, even though dinosaurs also had good vision, they couldn't strike first. This is because their brains lacked a capability that only we mammals possess. This is the second condition. The ability to plan. Before launching an attack, you need to plan. You can't just act impulsively like reptiles. How far is your prey? How far is the nearest dinosaur? Which route will you take? If your charge startles the prey, can you predict where it will run? Is that direction safe for you? What's your escape plan? These are things that regular vertebrate reinforcement learning can't handle. Reinforcement learning involves learning by doing, acting impulsively, when emotions drive us, and responding to situations as they arise. This approach works well in safe hunting environments, where failure isn't a big deal. But now, we find ourselves in a dangerous environment, where we must withdraw safely, if we miss our strike. This is the difference between street thugs and professional assassins. If you can plan before taking action, then you're not operating with just a lizard brain. To plan, our brain must be capable of simulating the environment. We need to run through our actions in the simulated environment of our brain before taking them. Of course, this requires a fast processing brain. This is our advantage as warm-blooded animals, unlike reptiles that slow down when it gets cold. So, that's not an issue. But simulation isn't just about fast brain processing. To simulate, you need the ability to imagine. You must be able to generate an environment in your brain and interact with it. Fish and reptiles still lack this ability, although birds later evolved this capability independently. This is a superpower. Our cave-dwelling mammalian ancestors, for some unknown reason, evolved a new cortex layer on top of the original brain cortex. It was this new cortex that gave us the power of imagination. From the earliest vertebrates, a type of fish, to the first mammal, spanning hundreds of millions of years, our ancestors went through various changes in appearance, body organs, and even living environments. But the changes in brain structure were minimal. The neocortex was the only new development. Early mammals had a small neocortex, but now in the human brain, the neocortex occupies 70% of the total brain volume. The neocortex is only 2 to 4 millimeters thick, but it has a large surface area. If you unfolded it, it would cover about 3 square feet, roughly the size of a small table. It exists in the brain through layered folding. The images you typically see of the brain are mostly the neocortex. The neocortex doesn't feel like something a carbon-based organism should have. In the mid-20th century, Vernon Mountcastle, later known as the father of neuroscience, discovered that the neurons in the neocortex, as well as their organizational structure, are completely uniform across the neocortex. The entire neocortex is essentially a result of replicating the same microcircuit over and over again. In today's AI terms, this is called scalable. If Mountcastle had seen modern AI, he would immediately say that the neocortex is essentially an AI neural network. This is the approach of silicon-based life. Other regions of the brain have fixed roles. In the neocortex, there are areas dedicated to vision, hearing, touch, pain, taste, movement, language, and even music. However, all these regions operate with the same circuits and computational methods. Their differences lie only in the input and output. For example, the visual area of the neocortex processes visual signals, but if a person is blind and lacks visual input, this area doesn't remain idle. It gets reassigned, perhaps to process auditory signals, which explains why blind people often have enhanced hearing. This is a form of general-purpose computation. Even more similar to AI, the neocortex engages in unsupervised learning. In nature, animals can't rely on supervised learning, because there's no teacher to label every object. They have to figure things out on their own. The neocortex does this, much like training a GPT model today. It reads part of the information, generates the next part on its own, and then compares the generated information with the actual data, reinforcing what's correct and adjusting what's wrong. For the brain, generation means simulation, which is essentially imagination. Generative AI has 2 steps: training and inference. It can't generate information while reading it simultaneously. And our brain works the same way. You can't read a book and imagine yourself having breakfast at the same time. Input and imagination must be separate. Before reading this book, I never realized that our brains can't simultaneously receive information and imagine a different scenario. Now, it seems remarkably similar to AI. No one fully understands how the neocortex generates information, just as no one knows how mammals evolved this structure. We only know that it excels at simulation. It can simulate various inputs, enabling us to imagine a scene, or even a concert, and allowing us to plan actions before executing them. This is why we are so good at filling in the blanks, why we are prone to false memories, and why we dream. Imagination is the third major breakthrough in brain intelligence. That's it for today's content. In the next part, we'll discuss model thinkers.
If you feel there is value in this, please like, subscribe to this channel, and leave your thoughts or suggestions in the comments section. Let's grow together and read more good books.